Hello everyone. I hope you all are doing good. This is me, Anubhav Sinha, with my groupmate Alexander George, and we're here to present you the dining philosopher's problem. Coming to the contents of it, we have the problem statement, problems, relevancy of dining philosopher problem in OS operating system, examples of dining philosopher's problem, and lastly, the solution of dining philosopher's problem. The philosopher problem states as follows. The first point, we have five silent philosophers seated at around a round table with bowls of spaghetti, and we see here forks are placed between each pair of adjacent philosophers. This is the whole start of the problem statement. Second point, we have each philosopher must alternately think and eat. Right, we have think and eat. Third, a philosopher can only eat spaghetti when they have both left and right forks. Here comes the first deadlock as we here see the number of forks and spaghetti is 5 and 5 each, which completely denies the fact that they or one philosopher can have left and right. Every philosopher needs to have the spaghetti with both right and left forks, which is the first deadlock. Fourth point is each fork can be held by only one philosopher. Each fork can be held only by one philosopher, which is easy. One philosopher can have one fork, but with the third point, we see another more deadlock here. Fifth point, it says after an individual philosopher finishes eating, they need to put down both the forks. But where will we get both the forks? Where will they get both the forks? If someone sacrifices to have the spaghetti, then only the individual philosopher will get both the forks. There's another more deadlock. Sixth point, a philosopher can only take the fork on their right or the one on their left as they become available, which means the spaghetti can be finished altogether or can be left on a half, and they cannot start eating before getting both the forks. Now we come up to the next slide, which is the problems. This problem was designed to illustrate the challenges to avoid the deadlocks. And here we see a solution was proposed in which each philosopher is instructed to behave as follows. Number one, think until the left fork is available when it is picked up. Think until the right fork is available when it is picked up. When both forks are held, eat for a fixed amount of time. Number four, then put the right fork down. Number five, then put the left fork down. Lastly, repeat from the beginning. This attempted solution fails because it allows the system to reach a deadlock state. Deadlock in here means a progress, a state which doesn't allow you to progress. This is a state in which each philosopher has picked up the fork to the left and is waiting for the fork to the right to become available for the left. With the given instructions, this state can be reached, and when it is reached, each philosopher will eternally wait for another to release a fork, which sums up that this attempted solution was a failure itself. Now I'll call my friend Alexander George.
Hello, good day to you all. Now I'll be guiding you through the rest of the slides. Now let's get into the next topic. It is relevancy of dining philosopher problem in operating system. Now we'll see how this dining philosopher problem plays a part in operating system. So we have like multiple devices such as desktop, laptops, mobile phones. They have multiple cores. Could be quad or octa core. So what happens is they have multiple programs running. So when there are multiple programs running inside these devices, what happens is they can lead to something called resource contention. What does resource contention mean? It means that when different programs try to access the same resource, now this may lead to resource contention, which may eventually lead to no progress state, which we call as deadlock, where there is no progress and both of the programs come to a halt and there is no progress. Now this is very much illustrated. This can be very easily illustrated using dining philosopher problem. So now let's take an example. Okay, so now let's take an example. Let us assume that there are two programs, program A and program B, running inside a device. Now let us further assume that these two programs are trying to access, let us assume the memory system at the same time. So now program A is saying that I want to access the memory, and simultaneously program B is saying that they want to access the memory. So now they both will sit and wait for each other. So this would lead to resource starvation. They are What does resource starvation mean is that they both get blocked out. They both are denied the access to a resource. Here in this case it is memory. So now this will eventually lead to a state called deadlock. Now what is deadlock? Deadlock means a state where there is no progress, like they are at a static point. Okay, now let's see how the dining philosopher problem can be viewed in terms of OS. Now, the forks in the dining philosopher problem can be seen as a resource such as memory, file system, etc. And the philosophers in that can be seen as programs or threads. Now, in the problem, we saw that two of the philosophers were trying to get access to the same fork. Now, as they were trying it simultaneously, they decided to step back and wait while thinking. Now, the programs in OS do the same thing. Like when two programs or more are trying to access the same resource, they decide to opt out and wait. And this leads to resource starvation, as I already explained, and ultimately leading to a state called deadlock where there will be no progress at all. Now let's take a look at the solution of dining philosopher's problem. Now let's take a semaphore to represent a fork. What is a semaphore? Semaphore is could be called as a variable here. Now we'll not get into much detail about semaphore. Let us assume that this is a variable. Now a fork can be picked up by executing a wait operation on the semaphore fork and released by executing a signal operation on the fork. Now, in the above structure, we see that the elements of the fork are initialized to 1. Now, why is it initialized to 1? Is because the forks are kept on the table and not picked up by the philosophers yet, and hence they are initialized to 1. Now, in the above structure, first wait operation is performed on fork 1, fork I, and then on fork I plus 1 modulus 5. This means that the philosopher I has picked up the fork on his sides. Then the eating function is performed. After that, the signal operation is performed on fork I and then on fork I plus 1 modulus 5. Now what does this mean? This means that the philosopher I has eaten and put down the fork on his sides. Then the philosopher goes back to thinking. Now this solution has some difficulty on its own. This solution is not perfect. There are some flaws in this solution. Now we'll discuss about it in the next slide. Okay, now before moving on to the flaws or difficulties with the solution, let us take a look at why the solution is a success. Now, why were the philosophers unable to eat? It was only because there were neighboring, at least two neighboring philosophers were trying to access the same fork. Neighboring philosophers in the sense the philosophers sitting next to each other were trying to access the same fork. Now, what our solution does is it eradicates or eliminates the possibility of any two neighboring philosophers eating at the same time. Now, this is how our solution works, and this is why our solution is a success. Now, under a certain circumstance, this solution becomes a failure and leads to a deadlock where there is no progress and it comes to a static point. Now, what is this circumstance? It can only lead to a deadlock only if all the philosophers pick the fork simultaneously, that means at the same time. Now, as the the philosophers pick the as all the philosophers pick the fork simultaneously, all the neighboring philosophers will also pick the fork simultaneously, which will lead to the previous problem, and hence there will be deadlock and none of them will be able to eat. Now this is how this solution is a failure only under a certain circumstance. Now let's come to the conclusion. Now it's written over here, the dining philosopher problem is another classic synchronization problem which is used to evaluate situations where there is a need of allocating multiple resources to multiple processes. As I said earlier, like when there are multiple programs trying to access the same resource, this is where dining philosopher problem comes in handy. Now we wouldn't have been able to solve these type of situation if the dining philosopher's problem had not come into the scenario. Now let's take a look at the references. Thank you. Arigato.